In this section, we're going to introduce variability into our processes. And here we want to understand why there's variability in systems, identify the components of the Kingman equation for approximating waiting times. These are the processing time factor, the utilization factor, and the variability factor. And we want to use the Kingman equation to calculate the average waiting time in front of a resource and explain why waiting times increase as resource utilization increases in processes with variability. Finally, we want to understand and discuss the impact of variability in lean production. Now, as we just learned, in a process where we know first that the processing times are exactly given, so 3 minutes for insert, 3 minutes for cut, and 6 minutes for sew, for example. And second, that there always are incoming parts, here's the material, ready for processing. What should be our focus? The bottleneck should always be working flat out, just as we saw here in the Gantt chart, where sew, our bottleneck, has to always be working. We also learned that there's an important relationship in Little's law, I equals R times T, where you have a given bottleneck rate and a minimum flow time through the system. There exists then a critical WIP where you have enough inventory to feed the bottleneck constantly, but not too much WIP that you increase the flow time. Now what happens if there's some variability in our system? Now there's two types of variability we're going to be looking at. And let's concentrate here on our bottleneck. So let's say there's some variability in our processing time, P. Varies a little bit. Sometimes you're a little bit more than 6 minutes. Sometimes you're a little bit less than 6 minutes in sew. And suppose there's some variability in the inputs coming in. The rate of the input into the bottleneck here is variable. What will happen? Well, given that, now we have to add a little triangle here to represent inventory buildup. We're going to start to get a little buildup of t-shirts, a little queue of t-shirts building up before our resource. It doesn't have to be the bottleneck resource. We'll have a little queue forming. Now, this is easier to imagine maybe in other examples. What about the cafeteria at lunchtime? You go for your lunch, you have to wait in line for food, then you have to wait in line to pay, for example. Here's a picture of a queue. Now, what's the inventory in this picture? It's the people of the inventory. And here's, of course, a classic example of a service process. So far, we've been looking at skateboards and t-shirts, which are these physical products. But if you have a service serving customers, the inventory, the people in the line who have to wait, they enter the process, get served, and leave. And if they have any waiting, that's very, very interesting for the person managing the process. And we wait in line every day. We wait at the post office. We wait at the checkouts. We wait in restaurants. We wait on the phone. So we all understand the impact of waiting. And why are we not served immediately? Well, the clear answer is, for example, lunch. Everybody comes to lunch at the same time. They have a certain number of cashiers, a certain number of people serving the lunch. There's more demand than the resources can serve. But the interesting point that we're going to see in this lecture is that even if there is enough capacity to serve the demand on average, variability in the system will cause queuing and cause waiting. As we saw before, the flow rate and flow time are critical measurements of our process, and they're related through Little's law by inventory equals rate times time. So let's add a little variability and see what happens to those performance measures. We're going to do this by looking at a simple model for queuing time. This is called the Kingman equation, first published by Sir John Kingman in 1961. The formula is an approximation for the average waiting time, abbreviated here as T wait, for a single resource with variability in the arrival of units to be processed and with variability in the processing times of that resource. There's three parts to our model. We've got the processing time factor, the utilization factor, and the variability factor. So first, looking at the processing time factor, here we have P. Now we learned that P was the processing time for a resource. In a system with variability, this will be then the average processing time. So on average 6 minutes, but it could be a little bit more, a little bit less. The resource capacity we learned was 1 over P, so average resource capacity. The maximum number of flow units an activity can process per unit of time, and here is one resource only. Resource utilization, we're now going to call this U. This is then the flow rate over the resource capacity. And finally, we have a new variable, V, which we're calling the variability factor. And this is a measure of the variation in, again, the arrival of units to the resource and the processing time for the resource. So in our course, we're going to be giving you V. If you're interested in this type of models, you can look into this in more detail. For example, the Cachon and Tervich textbooks, they use very familiar examples from service industries, and they show you how this factor will change. For example, if you're in hospital waiting rooms or in restaurants, and they do a good job of explaining the models behind this. So for us though, we've got then for the average waiting time in front of a resource in a system with variability, dependence on the actual processing time of our resource, dependence on how utilized our resource is, what is our resource utilization, and a dependence on the variability, how high or how bad is the variability in our system. And each one of these components will then contribute to waiting. Now let's just do one more review. This is the definitions we were given earlier. Processing time P, in this case now it's the average processing time, resource capacity 1 over P, the bottleneck, the activity with the smallest resource capacity, that defines our process capacity. And before we were given that the flow rate was equal to the process capacity. We assumed we had enough raw materials and we can sell every skateboard we made. And so if we're looking again at paint as our resource, we have variability coming in and we have variability in our process time. We saw here though that since our paint is our bottleneck, the utilization at paint in this situation is 100%. And we learned also that the resource utilization cannot be greater than 100%. Now let's see what happens for the waiting time in front of our resource paint. We have our T-weight equation, and it's given by P, which is 6, and our utilization, it's our processing time factor. Our utilization factor, well, 100%, so 1 over 1 minus 1. Don't forget, we have to, 100% is equal to 1 times a variability factor. And I haven't given that to you. Let's say this is equal to 1.2. 1.2. So what do we see here? Well, 6 times 1 over 0 times 1.2. This is equal to infinity. Our waiting time will be infinite in front of paint. How can this be? Well, what's actually happening is very easy to understand. Remember, we needed to keep paint working all the time. Why was that? Well, that's our bottleneck. It's got to keep working. It has no chance to take a rest. If we start to have variability, and backtrack, that's of course why this is 100% here. If we start to have variability in the process prior to the arrival of the skateboard, and into the arrival at paint, of the skateboards at paint. You know, sometimes they arrive a little bit early and sometimes a little bit late. Well, since paint is the bottleneck, it never has time to catch up for any boards that are late. And this means the queue over time will just keep growing and growing. Now you could say, but wait, you know, some of the boards are arriving early. It's true, but paint has to finish the boards that arrived late and that can never make up for the lost time. This is why the queue keeps going up. You can think of this in terms of concert tickets, for example. During a concert, the empty seats cannot be used later at another concert. So that capacity is lost. It's the same thing here. Once a board arrives late, the time where paint was taking a little break and waiting for it to arrive is lost. It can never make it up. And then some boards may arrive early, but then paint still has to take care of the boards that are in queue. And since it's the slowest resource there, with the utilization of 100%, the queue will just increase. Now this brings us to our first important point for use of the Kingman equation. For the Kingman equation to hold, the resource utilization must be less than 100%. So what does this mean exactly? This means that the resource has enough capacity to meet all the demand on average.